फर्स्ट पेज पे वाला पिछला. Very good afternoon, students. Can I see the number of students currently linked with the? Very good afternoon to all of you. Today in this live session of the science section and particularly physics part, I'll be discussing chapter number 13, that is magnetic effect of electric current. Students, it is very, very important to first clear the concept that magnetic field and electricity, they are inseparable. Normally, when you are studying magnetism, definitely we need to study electricity first. I hope that the maximum concept of electricity, current electricity at this junction of time are clear to you. Today we'll be discussing magnetic effect of electric current. So I have a presentation in which I'll be taking the topics slide by slide. So you concentrate on the content which is mentioned in the particular slide. So we'll be discussing only that content. And this content is in accordance with your Genius examination, mains examination, which will be conducted later. So let me come to first topic, that is magnetic field and field lines. Students, as it is very clear on the slide itself that the magnetic field, first we have to define what is magnetic field. So when it comes to magnetic field, it is just a region around a magnet where the force of attraction or repulsion can be detected. Now when we are talking about it is a region where the force of attraction or repulsion can be detected, it means what? How to detect the magnetic field? Now, if we are having some magnetic material or specifically a magnet which is placed inside the magnetic field, definitely a force will be exerted on that material. So as it is clear, you can see here, magnetic field around a magnet can be detected by using a magnetic compass needle. So all of you are aware that what is a compass needle. A magnetic compass needle, it itself is a magnet. It's a small magnet having north and south polarity. As it is clear in the diagram itself, one polarity which is mentioned in red is north pole and the other one is south pole. So if we want to detect a magnetic field, we need to make use of a magnetic compass needle. Now, what is magnetic field lines? What are the magnetic field lines? Now the concept is, what are the magnetic field lines? Now field lines, they will be representing a magnetic field. तो आप सबको पता है कि मैग्नेटिक फील्ड अगर है तो उसको रिप्रेजेंट कैसे किया जाए. तो मैग्नेटिक फील्ड को रिप्रेजेंट करने के लिए हमें मैग्नेटिक फील्ड लाइंस की हेल्प लेनी पड़ती है. So what are the magnetic field lines? They are just the path around a magnet along which the north pole of a magnet compass needle tends to move. So as just I have shown in the previous slide, that we can make use of a magnetic compass needle to draw the magnetic field lines. Now the second point which is in front of you, that is magnetic field lines around a magnet can be observed by sprinkling iron filings around a magnet. So this is one of the method by which we can observe the magnetic field lines. So we can make use of iron filings and just tap on the board. What you will observe is the pattern which is surrounding the magnet, and this particular pattern will show you the formation of magnetic field lines. So on the left of your screen you can see these are the magnetic field lines which are created with the help of iron filings. Now on the right hand side in the slide you can see the magnetic field lines which are actually drawn. So the lines, they are moving, they are coming out of north pole and entering into the south pole. So we will be discussing some properties also now. We'll be discussing some properties of magnetic field lines. This is very, very important. There are some questions also which are asked in examination related to the magnetic field lines. Let me take first property, that is magnetic field lines, they emerge at the North Pole and merge at the South Pole, which is written, that is the first point. Now the second point, if you can see, magnetic field are closer at the poles. Now magnetic fields lines are closer at the poles means it represents strong field. So strong field, it is created near the north and south polarity, and in between, if you see the spacing between the line, it increases and it represents a weak field. So in the center outside, you can see there is a weak field which is created, and near the poles there is a strong field which is created. Third point, magnetic field lines do not intersect each other. Very important property. Magnetic field lines, they never intersect each other. This is very important, because when we talk about magnetic field lines, and if we talk that, there is a question also, why magnetic field lines, they never intersect each other. So why the magnetic field lines do not intersect each other? So this is a very important question. And if we want to answer this question, what is the explanation for this? Suppose if two magnetic field lines, they intersect each other, then what will happen? There will be a point of intersection. So if there is a point of intersection, we can draw two tangents at a particular point. If we draw two tangents at a particular point, it means they will be showing two directions of magnetic field, and that is not possible. It is impossible. At a single point, we cannot have two directions of magnetic field. So the question is, why two lines, they never intersect? The answer is very simple. The magnetic field lines never intersect, because if they intersect at a particular point, there will be two directions of magnetic field, and which is not possible. So let us move further now. Magnetic field due to current carrying conductor. So this is very important. Now magnetic field due to a current carrying conductor. So when we are talking about magnetic field due to current carrying conductor, it means magnetic field which is generated around a current carrying conductor. It is very important, because earlier in the beginning of this live session, I told you that magnetic field and electricity are inseparable. We cannot separate these two phenomena. So you can see clearly in the screen, if we see here, current is flowing in two different directions. If on the left side, if you see, current is going from north to south, and it is also going from south to north. And if we place a magnetic needle, compass needle, very close to this wire, what you will observe is there is deflection in the magnetic compass needle. So what does this mean? It means that there is a field which is created around a compass, around the compass needle, and this field is created because of current electricity. So if you see the pattern of the magnetic field lines around a current carrying wire, it is clearly, you can see they are in circular loops. We'll be discussing in the next slide what is the basic rule which decides the direction of magnetic field lines around a current carrying conductor. So there are certain points which I want to mention here. If you see, direction of the current in the right side on the figure is going from the south to north. And if I draw the magnetic lines, that will be concentric circles around the wire. And this is given by a rule which you are aware of, I think. I will be discussing the rule also. Let me come to next slide. Right hand thumb rule. It is very important. Right hand thumb rule. Now you can see the direction of magnetic field around a conductor is given by right hand thumb rule. Now what is right hand thumb rule? It is very simple. It states that if a current carrying conductor is held in the right hand such that the thumb points in the direction of current, then the fingers wrapped around the conductor shows the direction of magnetic field. So you can just take your right hand and just stretch, you just curl the fingers, and the thumb here, you can see in the diagram, it is pointing in the direction of current, and the curled finger pointing in the direction of the magnetic field. And you can see very well below this hand, you can see the pattern of magnetic field lines. So student, I hope it is clear from you, from this particular diagram, that what is actually the rule which governs the direction of magnetic field lines around a current carrying straight conductor or a wire. So let us move further now to the next slide. Now you can see magnetic field due to a current that is through a circular loop. Now this is very important. Earlier it was a straight conductor and we were discussing about the magnetic field pattern around a straight conductor. Now it is a circular loop here. Loop can be created by just molding a wire in a circular form. Now what will be the pattern of magnetic field lines around this circular loop? So you can see when a current is passed through a circular conductor, that is a loop, magnetic field which is produced is in the form of concentric circles. So you can see again here the concentric circles are produced on the both ends here around the conductor. Now if you see the pattern at the center, if you see what is the pattern of the magnetic field lines, the magnetic field lines are almost straight in the center of the loop. You can see a battery which is drawn below this diagram, and there is a flow of current through this loop, and when the current is flowing, again the pattern is generated, and when you go exactly at the center of this circular loop, you will find that magnetic field lines are almost straight. So near the wire you will see the concentric pattern, and at the center of this circular loop you will find that the lines are almost straight. So it is very, very important. So you can see the point here, second point, that is towards the center of the arc of the circle become larger and appears as a straight line. Let us move to the next slide now. Magnetic field due to current in a solenoid. Now it is very, very important aspect here which we have to discuss, that is a solenoid. Now the basic thing is, what is a solenoid? So solenoid, now what is a solenoid? A solenoid is a circular coil of a wire in the shape of a cylinder. So you can just take a copper wire and just give it a shape which is just mentioned in the solenoid. So it is a cylindrical form of a copper wire which will create a solenoid. So it is clear here. Now when we pass current through this solenoid, what you will observe is there will be production of magnetic field around this solenoid, and now it will start behaving like a bar magnet. So until and unless we pass current through this solenoid, before passing it does not create any field, but after passing the current, immediately it start creating a field around it. So you can see when current flow through the solenoid, it behaves like a bar magnet. Now third point, if you see, the ends of a solenoid behaves like north and south poles of a bar magnet. Now again, now I just told you that this solenoid start behaving like a bar magnet, and bar magnet have two poles, one is north and other is south, and these north and south polarities, they will be created as per the direction of the current. If current is flowing from one direction to other direction, polarities are north and south. On one side there is north and other side it is south. If we reverse the direction, the polarities will be reversed. Now in the diagram you can see the magnetic lines, they are flowing from north to south, and a very interesting aspect about these magnetic field lines is they are continuous curves. Earlier I have not mentioned this when we were discussing the properties of magnetic field lines, but now it is clear from curves. Why we say that they are continuous curves? Because outside the lines they are moving from north to south, but inside you can see the lines, they move from south to north, making a continuous curve. So this is a very important property, that magnetic field lines are continuous curves. Now you can see the next point. The magnetic field produced by a solenoid is similar to the magnetic field produced by a bar magnet. So it is same, the pattern is same. The strength of the magnetic field, this is very important. strength of the magnetic field depends upon the strength of the current. So it is very, very important to note it down that the strength of the magnetic field will depend upon the strength of the current. Greater the value of current, greater will be the magnetic field. And number two, that is number of turns of the coil. This is another very important point. If we keep on increasing the number of turns, definitely the magnetic field becomes stronger and stronger. So this is very important. These are two very important points to be noted down. That is, the strength depends upon current, and it also depends upon the number of turns of the coil. Let us now move further. You can see here in this slide I have just shown you, this is a solenoid. You can prepare this solenoid at home also by just taking a copper wire and give it a cylindrical shape. It becomes a solenoid. So and later on we will be discussing that what is the difference between a solenoid and a permanent type of magnet, or we call it a electromagnet. So this is the diagram for a solenoid. Now the point comes here, electromagnet. Now what is an electromagnet? This is very important now because it has commercial use also. So what is an electromagnet? Now you can see as we just discussed that we have a solenoid and it is creating a field inside and outside. Now a strong magnetic field inside a solenoid can be used to magnetize a piece of a magnetic material like a soft iron when placed inside the coil. If you take a magnetic material like soft iron and place it inside a solenoid, this combination becomes an electromagnet. And why we call it an electromagnet? Because we are making use of electricity here. Because until we are passing electricity through this combination of soft iron and a solenoid, it will not exert any field. So as soon as we pass the electricity, it becomes an electromagnet and becomes a strong magnet. So the electromagnets are always strong magnets. So the point which is now next point is, if electric current is passed through a wire wound around a piece of soft iron, it gives like a magnet. I just told you, such a magnet is called a electromagnet. You can see the diagram on the right hand side. You can just prepare an electromagnet at your home. Also, it is an activity for you. You can make use of a simple battery. You can make use of a switch, which is a key, and you can just wrap a wire, copper wire around a nail. To just you can just, this is a very simple activity on the right side. You can do this activity at your home and give me feedback. I'll be sharing my email ID and my WhatsApp number. You can send your queries, or if you have any doubts, you can share it with me. Definitely I'll be replying to your queries. So now we are having a very important topic from the examination point of view. That is Fleming left hand rule. Fleming left hand rule. It is very important to know and to understand the concept of Fleming left hand rule. Now, when we talk about the magnetic field, we will be talking about the force which will be created by the magnetic field. Now, when we talk about the force, it means definitely some force will be exerted on current carrying conductors or wires when they are placed inside a magnetic field. So if you see the diagram on the left hand side and right hand side, it is explaining you the Fleming left hand rule. Now I'll just read the point which is mentioned here. That is, it states that if we hold the thumb, forefinger and middle finger of the left hand perpendicular to each other, such that the forefinger, you can see the forefinger here clearly, forefinger points in the direction of magnetic field, the middle finger points in the direction of the current, and the thumb will be pointing in the direction of the force of the conductor, which will be exerted actually on the conductor, current carrying conductor. So you just remember that you will be utilizing your left hand and you will be stretching these three fingers, which is your thumb, the forefinger and middle finger, and accordingly you can see the directions here. That is, forefinger pointing in the direction of magnetic field, middle finger pointing in the direction of the current, and the force is given by the direction of the thumb. So we'll be utilizing this concept, and we'll be utilizing this to tell the direction of force in the the coming talk. So let us move further now. Force on a conductor carrying current in magnetic field. So we will be now implementing this Fleming left-hand rule to explain the direction of the force which is practically exerted on a conductor. So just you can see the diagrams which are given down here in the slide. On the right side, it is very clear and obvious that when we are placing a conductor which is inside a magnetic field, it is a current carrying conductor inside the magnetic field. Now you can see the polarities, north and south polarity. If we place now there is a uniform field between these two poles because it is a U-shaped magnet and it is creating a uniform field. And uniform field along with the current carrying conductor, now if we apply Fleming left-hand rule, we will find out that the direction of the force will be pointing outwards. So if I reverse the direction of the current, just see the right diagram, right side, the diagram on the right side. If we reverse the direction of the current, the force will be pointing towards the U-shaped magnet. Now, here it is pointing outwards. If I reverse the direction of the current, it will be pointing inwards on the other side. So you have to just stretch your fingers and point the three fingers in direction which have been mentioned in the Fleming left-hand rule. There is a practical demonstration also which you can see on the left side. So there is a current carrying conductor. Some wires are being used here and current is flowing through a conductor, and this conductor is lying inside the horseshoe magnet, U-shaped magnet, and inside the uniform magnetic field there will be force exerting on this conductor and the direction will be decided by Fleming left-hand rule. So I hope that this rule is clear to you with the help of these two diagrams. You can stretch your fingers practically and take a wire, stretch your fingers accordingly and see in which direction the force is pointing. So let us move further now. This is very important point to be noted here. That is the force on current carrying conductor. Now, another very important concept, that is electromagnetic induction. So, since this is a time-bound lecture, I have to just see the time also. We'll be completing the topics which I have just taken now. Electromagnetic induction I will be completing, and then I'll be sharing you my email ID and my WhatsApp number. May I know the timings? What is the time exactly? Okay, right. Thank you. So electromagnetic induction. Now, what is electromagnetic induction? This is very, very important concept. Michael Faraday, he explained the concept of electromagnetic induction. And electromagnetic induction, as the name itself, induction. Induction means to induce, to generate. Now, motion of a magnet with respect to a coil or a change in the magnetic field induce a potential difference in the coil and produces induced current. Now this is very important. Now earlier in the beginning of this live lecture, I told you that we cannot separate magnetic field, magnetism and electricity. The concept was realized by Faraday. He introduced this concept that we can produce electricity in a wire by just changing the magnetic field. So there are two diagrams which you can see in the screen here. From the diagram itself, it will be very clear to you. Now what we are doing is, we are moving a bar magnet near and outwards a coil. So when we will be moving a bar magnet towards the coil, what will happen? Magnetic field will be changing. Now it will increase. When we are bringing a magnet close to the coil, magnetic field will increase. And there is a very important term which we make use of is flux, magnetic flux. So the flux is the magnetic field lines, number of magnetic field lines associated with any conductor or a coil. So as soon as I move a bar magnet towards the coil, what will happen? Flux will increase. Flux will increase means magnetic field associated with the coil will increase. When there is increase in the magnetic flux associated with the coil, there will be production of electricity in the coil. Very important to be noted here. what we have done is we are not supplying any current from outside. We are not supplying any current from outside. We have not made use of any battery or a cell. We can see the deflection there in a galvanometer, which will be attached with the coil. As soon as I move a bar magnet, you will find that there will be a deflection in the coil. What does this mean? It means that some current has been generated in the circuit, and this concept is called electromagnetic induction. We are inducing current in the coil with the help of changing magnetic field. You remember this point, this is very important. By changing magnetic field, you can produce current electricity in a coil or a wire. What you have to do is just you have to ascertain that there is a change in the magnetic field. Now you can see in the second diagram, which is just below this first diagram. Now what we are doing is we are taking bar magnet away from the coil. Now when we are taking it away from the coil, what does this mean? What is happening now? The magnetic field is decreasing. Now magnetic field is decreasing. Now when magnetic field is decreasing, it means what? Magnetic flux is decreasing. Again there will be production of EMF or current in the coil, and this is very, very important. You can see here again current is produced. You can see the deflection there in the this galvanometer. It will be showing deflection in the other side. It means what? That we are able to produce current in the coil by moving a magnet away from the coil also. So there are two concepts which you have to remember now. What we have done in the first diagram, we were moving a bar magnet towards the coil. It means we were increasing the flux. Now in the second diagram, what we are doing is we are taking this bar magnet away from the coil. What we are doing? We are decreasing the flux. It means if we are either increasing the flux or either decreasing the flux, electricity is produced in both the cases, but the direction of the current electricity is different. You can see on the first diagram the deflection is on the one side, and in the second diagram you can see deflection is on the right side. It means current is produced, but it is in both cases current is produced, but the direction of the current is different. So this is a very important point to be noted here. So the concept of electromagnetic induction can be realized by varying the magnetic field, which we have just discussed. Now there is a second case also, how we can do it again. You can see now we are not making use of a magnet here, we'll be making use of a battery. So in the diagram you can see very clearly we are making use of a battery, a key and a coil number 1, and on the other side you can see coil number 2. Now why we have arranged these coils very close to each other? Because when I will close the circuit, close means I will put on the key K, what will happen? Current will start flowing in coil number 1. Now as soon as current starts flowing, magnetic field is generated. You all know magnetic field will be generated, and this magnetic field get associated with coil number 2. This is very, very important now, because coil number 2 is very close to coil number 1. As soon as I make changes here in coil number 1, magnetic field of coil 1 get associated with coil number 2. Now what we will observe practically, you will observe that there is deflection in the galvanometer. And what does this indicate? This indicates that there is production of current in coil number 2. So what we are doing here is we are creating current in coil number 2 with the help of coil number 1. Now you can see a coil number 2, we have not attached any cell or a battery. It is only an arrangement in which we are generating current electricity by just changing the magnetic flux. And again I am repeating this term which is very important, that is magnetic flux. Number of magnetic lines associated with the conductor. So you can see here on the right side there is a diagrammatic representation also. Practically the coil number 1 and coil number 2. Coil number 2 is attached with the galvanometer or either any electronic voltmeter. You will see the deflection and this deflection will prove that current can be generated in a conductor with the change in the magnetic field. So student, I hope the concept is very clear to you. So these two slides, this slide and the previous slides, they are very, very important because this concept will be utilized for the production of electric current in generators. Now the topic generator has been eliminated from class 10, but earlier, since it was the part of your syllabus, so we used to discuss the working of generator with the help of the Faraday law, that is electromagnetic induction, and it is very, very important. In higher classes you will be utilizing these concepts to discuss the working of a generator. So any queries or any doubts will be taken on your doubts. You can send me on my email, personal email, or either you can share it on my WhatsApp number. I'll just share my WhatsApp number. I'll be taking one more slide here. But before, I would like to share my WhatsApp number. Would it be able? Okay, I'm just writing on the chat box. You just see. Principal SVM Dhuri @gmail.com, and my contact number. So, okay, Yogesh is saying which concept Yogesh is talking about. Some concept is not summarize the experiment. Okay, okay. Yogesh, I will be summarizing the concept to you. I hope you are talking about electromagnetic induction. Okay, right. Can I have the slide, please? Okay, Yogesh, now you can see the concept was of electromagnetic induction. So, in simple words, what I will just want to explain you is, we can produce the electric current in a coil with the help of changing magnetic field. This is the concept. Faraday very clearly told this concept that if you can make some changes in the magnetic field associated with the coil, you can produce a current in a conductor. तो आप ये देख सकते हो, Yogesh, you can see very clearly in first and second diagram that I am just doing one thing. I am just moving a magnet. I am either moving magnet close to the coil, or either I am taking magnet out of the coil or away from the coil. So when I am using a bar magnet and moving it towards the coil, magnetic field associated with this coil will increase. Magnetic field associated with the coil will increase. It means the magnetic field which was generated by the bar magnet, and this field is now associated with the coil. So when I am moving the bar magnet towards the coil, magnetic field associated with the coil will increase, and there will be production of current. So this is the concept which Michael Faraday gave, that you just change the magnetic field associated with the coil, you can produce current. So in the second diagram, you can see very clearly, I am taking a bar magnet away from the coil. Now what is happening here? I am decreasing the magnetic field associated with the coil. The coil is not attached with any battery or a cell. What I am doing is just moving a bar magnet away. Now, as soon as I am moving the bar magnet away, what is happening? The flux associated with the coil is decreasing. So if the flux is decreasing, what happens? Electric current is again generated. So this is very important to note that magnetic field and electricity, they are inseparable concepts. They are interlinked with each other, and this thing was realized by Michael Faraday, and what it was a revolution in the field of electricity, because it was only after Michael Faraday gave this law we created generators to produce electricity. Because earlier we used to study magnetism and current electricity separately, but when Michael Faraday introduced this concept, that, which is electromagnetic induction, it revolutionized the concept. And the concept was very clear that we cannot separate electricity and magnetism. And when we are not able to separate magnetism and electricity, it means they both can be studied combined. So means it is a combined study now. So in this diagram and the further diagram, you can see the same concept is realized in the second next slide also. The same concept is realized. Earlier we were moving a magnet, but now we are not moving a magnet. We are just changing the magnetic field. Now how it is changed here, you can see it is a battery here, and as soon as I insert a key in K here, you can see the diagram K represent a key. As I close the circuit, current start increasing, because it takes certain time for a current to reach its peak value. So as soon as the current is increasing, magnetic field will be increasing, because it will take certain time. It might be in seconds, fraction of seconds, but it will take some time to reach the maximum value. So it means the current is increasing. As soon as the current is increasing, the magnetic field which is created by coil 1 will be associated with coil 2. And when the magnetic field, changing magnetic field is associated, or it is associated with coil number 2, immediately current will be produced in coil number 2. So one point which you have to note down, or you have to just memorize it. The point is, we need changing magnetic field. We cannot induce current in the coils by stable magnetic field or stationary magnetic field. It need to be varying magnetic field. And now how it can vary, we can make use of the gadgets which are just shown here in the diagram itself. We are making a use of a battery, or on the right side you can see I'm making use of an alternating source also. You can see in the right side in the diagram there is a symbol here which is just an line which is shown. It represents an alternating type of signal or alternating type of voltage. Alternating means changing. So when the current is changing, magnetic field is changing. So you memorize one point. It will be discussed in higher classes also. Whenever you are changing the magnetic field, you can induce electric current. If you are not able to change the magnetic field, you might not be able to create a induced current. So induced currents can only be produced when you are varying the magnetic field. You remember this concept. So I hope now it is clear to you. Still I will be taking your queries. I have just in the message box I have written my email ID, and I have shared my WhatsApp number also. You can send your queries to me, and in coming lecture, next lecture, we will be discussing some other concepts of electromagnetic induction or the magnetic effect of current. So since this lecture is time bound, I'll be taking some other slides in coming lecture. Thank you very much. I hope you have enjoyed this lecture. Thank you and good afternoon to all of you.